So in this video, let us discuss about the relationship between the focal length and radius of curvature of a concave mirror. Suppose this be a concave mirror and this point is the pole of the concave mirror. And let C be the center of curvature of the concave mirror, and the axis passing through this center of curvature and pole is called the principal axis. That is, this dotted line is the principal axis. We have, let's mark focus, principal focus, somewhere between P and C. We need to actually, the distance between C and P is the radius of curvature, we call that as R, and the distance between focus and pole is called the focal length F. We are interested in this video, we are interested in finding a relationship between F and R. So how will we do it? And we know any ray, by theorem, any ray which is passing parallel to the principal axis like this always passes through the focus. That is, any ray which is parallel to the principal axis after reflection on the concave mirror passes through this focus. And this is the normal. Let this point be some A, and we have the normal to a spherical surface will always be the line passing through the center of the sphere. Or in a circle, the radius is always normal to the surface. That is, this angle will always be 90 degree. And now we have this is the incident ray and this is the reflected ray. So the angle between the incident ray and the normal is the angle of incidence I, and the angle between the reflected ray and the normal is called angle of reflection R. I is the angle of incidence, comma, R is the angle of reflection. Clear? Now let's drop a perpendicular from A to the principal axis like this, and let's call that point as M. See, this curvature of this sphere is very small, so that we can consider this length MP. This MP can be approximately equal to 0 because the angle I and R are very small. So this M and P always almost coincide, but for convenience, let's draw this way so that there is a little distance between MP. Actually, the distance between M and P is 0. Now, this is actually 90 degree. Now, actually, if MP equal to 0, we have Fm approximately equal to Fp. Clear? These two distances are Fp and Fm are same. Now, let this angle be some alpha. Let's assume this angle. Before that, let's consider triangle ACM. In that triangle, we have angle ACM. Angle ACM is equal to alpha. Let angle ACM equal to alpha. But we know I is equal to alpha. Clear? Because this green ray and the principal axis are parallel. So they form the alternate interior angle. This is the I and this is alpha. So this I and alpha remains the same. The reason for that is this ray is parallel to principal axis. Also, we have I is equal to R because angle of incidence is equal to angle of reflection. That is angle of incidence equal to angle of reflection. That is laws of reflection. According to laws of reflection, we have angle of incidence equal to angle of reflection. Connecting these two, we have I is equal to R is equal to alpha. Clear? Now, if you consider this triangle ACF, let me draw that triangle. That is this is A, this is C, this is F. Actually, this angle is alpha and this angle is R. And you know this is the exterior angle. Exterior angle will be sum of the other two interior angles. That is, we have this angle will be alpha plus R. See, any exterior angle will be sum of the other two interior angles. This is actually R. Okay. R. So alpha plus R will be this angle. That is equal to, we know we can write alpha instead of R. So this will be alpha plus alpha, which is equal to 2 alpha. So this angle will be 2 alpha. Clear? Now, if you take the trigonometric ratio tangent, that is the trigonometric ratio tangent of the angle alpha from triangle ACM, we have tan alpha will be opposite side, that is AM. We are considering this triangle ACM, right? That is this triangle. That is tan alpha will be AM by CM. Clear? Let me write AM as AM itself. Then, but we know CM is actually R. Clear? Because we already said this MP is almost 0. So that CP is equal to CM. CP equal to CM, which is equal to R. Clear? Call this as equation number 1. Now, if you consider triangle AFM, consider triangle AFM, you have tan 2 alpha, this angle is 2 alpha, is tan 2 alpha equal to AM, opposite side, divided by FM, which is equal to, like I said, FM is equal to FP, which is equal to F. So AM divided by F. Call this as equation number 2. Now, if you divide these two equations, that is equation 1 divided by equation 2, you will get on the left hand side it is tan alpha divided by tan 2 alpha is equal to AM divided by R divided by AM divided by F. Now this alpha and 2 alpha are very small, so that tan alpha approximately equal to alpha, because alpha being very small. Similarly, tan 2 alpha, you can substitute 2 alpha for tan alpha. That is approximately equal, because we have the property tan theta is approximately equal to theta for small angles. Clear? For small angles, tan theta is approximately equal to theta. So I can rewrite this as alpha by 2 alpha is equal to, this is equal to AM divided by R into F by AM. Reverse this and multiply. So AM and AM will get cancelled. This is equal to alpha and alpha will get cancelled. So 1 by 2 is equal to F by R, which means F is equal to, taking this R to the left, F equal to R by 2. That is, focal length is equal to half the radius of curvature, or you can write R is equal to 2F also. Clear? That's the relationship between radius of curvature and the focal length. Now let us discuss about the relationship between radius of curvature and focal length of a convex mirror. Suppose this be a convex mirror with a pole P, and this line is the principal axis, and we know if a ray passes parallel to the principal axis, it will get reflected like this, and we feel that the ray is coming from the point called the focus. Clear? So let this point be the focus. And as I said before, the normal to a spherical surface is always the radius of the spherical surface, so that this normal passes through the center of curvature. So we have this length is the focal length, that is PF, the distance between focus and the pole, and this length is the radius of curvature R. So we need to find the relationship between F and R. We know the angle between, this is the incident ray and this is the reflected ray. We know the angle between the incident ray and the normal is the angle of incidence, and the angle between the normal and the reflected ray is the angle of reflection R. That is R. Now see, these two are vertically opposite angles, so this will be R itself, angle of reflection, because this normal and the extension of the reflected ray are vertically opposite. And let me call this angle as alpha. Okay, but we know angle of incidence is, this I is the angle of incidence equal to angle of reflection. This is according to laws of reflection. Now let me drop a perpendicular, let's call this point A. Let me drop a perpendicular from A to the principal axis, and let me call this point M. Here this PM is very small, the distance PM is very small. This P and M almost coincide, so that PM is approximately equal to 0. Actually, this FP is equal to FM. Since this PM is very small, that is PM is 0, and that is the focal length F. Also, CP is equal to, that is CP equal to CM, which is equal to R. It's better to write approximately equal to. Okay, equal to R. Now consider triangle, let's say AMF. Triangle AMF. See, this angle is the exterior angle of this triangle ACF, like we said before. So that we have angle AFM, that is this angle AFM, is equal to sum of the other two interior angles, that is R plus alpha. Call this as equation number, let's say 1. Now if you look here, that is, let me call this x dash. If you look at XA x dash, that is this angle and this alpha remains the same, because it's like this. Clear? This is alpha, this is I. They are actually the corresponding angles because these lines, this green line and the principal axis are parallel to each other. And this xc is actually the, x dash c is the normal. It's a straight line. So these two angles are same. So I can write I is equal to alpha. So when you club these two things, you will get I is actually R and R is actually alpha. Both, all of them are equal. Now I can write angle. Now if you substitute this values in the equation 1, or if you compare this with equation 1, you have AFM is equal to, instead of R, I can put alpha, alpha plus alpha, which is equal to 2 alpha. Clear? So this angle will be 2 alpha. Now consider, again consider this triangle AMF. AMF, you have, if you take the trigonometric ratio tan 2 alpha, that is tan of this angle, tan is equal to opposite side AM divided by MF or FM. That is tan of 2 alpha is equal to AM divided by, but you know FM is equal to the focal length F. Call that as equation number 2. Now consider, let's consider this triangle AMC. AMC. And if you take the value tan alpha is equal to opposite side AM by, I'm considering this triangle, okay, AM by MC, which is equal to AM, write it as AM itself, by MC, or CM is actually R. Call this as equation number 2. Now, if you divide equation 1 and 2, that is equation, call this as equation 3, okay. Equation 3 divided by equation 2, you will get, on the left hand side it will be tan alpha by tan 2 alpha is equal to AM divided by R whole divided by AM divided by F. But the alpha being very small, we can write tan alpha approximately equal to alpha and tan 2 alpha approximately equal to 2 alpha, because alpha being very small. Very small. Clear? So this will become alpha by 2 alpha is equal to AM by R. You can reverse this, take the reciprocal and multiply, so that F by AM. This AM and AM will get cancelled. Alpha and alpha will get cancelled. So 1 by 2 equal to F by R. That means, again we get the same relation. F is equal to, taking this R to the left, F is equal to R by 2. So this equation works for both the convex and concave mirror. Or you can write R is equal to 2 times F. Clear?